First, I'm going to tell you about OpenMP 4.0 and where we might go from there. As I mentioned, basically just a couple weeks ago, OpenMP 4.0 was approved. We haven't actually issued the press release yet, but it's actually official nonetheless. We've been working on this for a while now. It's been 3 years since we released 3.1, but the entire time we were working on 3.1, we were also working on 4.0, so it's been more like about a 5-year process, which is actually pretty fast, all things considered, given that we also did release an intermediate version in there in terms of how language standards move forward, but that's maybe another story. Anyway, we're not done, so if there's things that you'd like to see in there, like reductions on arrays in C and C++, yes, we're aware of that one, and we do plan to add it in there, but there are many things that if you're looking for, we're able to add them. So 4.0 does address many major issues. In fact, 3.0 added tasking, and that was a pretty significant addition. 4.0 adds 2 new types of parallelism to OpenMP. So just in that axis alone, 4.0 is twice as much of an advance as 3.0. And we added a whole bunch of other stuff, whereas most of what got added to 3.0 was tasking. We use a track system to kind of track where we're going, and a software carpentry thing that kind of follows along there. There we're not actually tracking bugs, although we do have some things that are kind of bugs in the spec. We ended up actually having 106 tickets. That doesn't say that much because some of them are small, some of them are very large, but it is a fair amount of stuff. Anyway, so we've already begun working on 5.0. This is what we added. So we added device constructs, which are actually support for what you would probably be most commonly thinking of as accelerators. So you will soon be able to use OpenMP for programming things like use of GPUs on your heterogeneous nodes. The language supports it. Where the implementations are is another discussion that I'm not going to get into tonight. And we added SIMD constructs. So these are the 2 new forms of parallelism that we've added to OpenMP. We've added support for something called cancellation. I'm not sure how much I actually included in this talk about that, so I may have to fill some in on that. But that's basically the ability to, within a region, decide that you want to abort the region. Okay? Primarily, we were adding that for the purposes of supporting error handling. But it actually, in the context of tasking, improves the expressiveness of the language pretty significantly. Relating to tasks, we added a concept called task groups. So when Paul was going over tasking, he told you about how with barriers you can have kind of this way to synchronize across all tasks within a parallel region. And with task weight, you have an ability to do synchronization at a shallow level, just at the siblings at that level of tasking. Task groups allow you to group up a set of tasks that are created in a dynamic context, cause all of those tasks, whether they're at that level or if they're descendants at that level, to be waited for at the end of the task group. In addition, we've added something called task dependencies that now allow you to specify, do not execute this task until this previously created sibling task has completed. Paul alluded to some of the thread affinity control, and I'll go into some of that. I've already mentioned the user-defined reductions. I don't know if I have anything on it in here. We've actually had those pretty well set for a while now. And we've begun moving to supporting Fortran 2003. You might say, well, 2003, what about 2008? Well, pretty much none of the vendors other than Cray support 2008. We've added support for array sections, which is important for task dependencies and also for the accelerator device constructs. And a little thing that we added that's pretty important in many ways is sequentially consistent atomics. And this is consistent with what exists in the C and C++ specs. And then a little thing we added is that you can now actually set an environment variable that says print out the initial values of the internal control variables. All right, so probably the thing that's caught the most interest among people is the support for devices, is these device constructs. And the basics of it is that you use this target directive to offload a region of code to a different device. So you just say, okay, I want to target some device, and I can put some clauses on it, and there's a default device. Typically, we expect there to be, say, one GPU, but you can actually have multiple GPUs on. And then that will say, take this structured block and execute it over there. All right? And the compiler is responsible for outlining that structured block and generating code that's appropriate for that other device. All right? And it also creates a new data environment in the enclosing data environment on the device. All right? And so there's various ways that through the clauses that you can say, okay, I need to move this data over there, and also, do I really want to offload it? So is there enough work in this structured block to justify moving it over there? You have a device clause that says that allows you to specify, well, I want to execute it not on the default device, but on device number whatever. And map is the thing that says, I want to map this variable to the device, and I want to do it so that I either move the initial data values, at the end of it I can move the data values back, or both. And we have a couple other constructs that are actually pretty important. One is the target data construct. So if you're familiar with accelerator programming, you'll know that data movement over the device is really the big cost. And so you want to try and minimize that. But you may have naturally in your code regions that you don't want to offload, even though the set of regions that you want to offload are the only ones that touch a piece of data. And so the target data construct allows you to say, move this data over there and keep it over there until the end of this region. And then all the target regions that you encounter within that target data region have that data available to them. And then the update construct allows you to say, okay, I've moved data over there either through the map clause on a target construct or through the target data construct, and now I want to move it back to the host, or I want to do something to update it on the device. All right, so you have a structured block, and in that structured block you have a function. All right, so well, you want to make sure that a version of that function that is compiled for the device exists. So that means where you declare the function and where you define the function, you want to tell the compiler, I need a GPU version of this function. And so what you do is you use this target declare directive to annotate those declarations and definitions and tell it, okay, here's what you need to do, what you need to generate the device code for. Importantly, if you're familiar with GPUs, you'll know that you can have multiple warps, and it's often very difficult to synchronize across those warps, all right, across, well, actually thread blocks. Well, the teams construct allows you to now say, I'm going to create multiple thread blocks within this target region, and those thread blocks now don't have any synchronization except for the end of the target region. And so that gives you this concept of creating multiple thread blocks. However, you may actually want to take a loop that's in your target region and distribute it across your thread blocks. And so now you can use this distribute construct to take that loop and distribute it across it. And then there are, as I kind of indicated earlier, many, many new combined constructs that allow you to do things like target, teams, distribute, because if you think about it, that's a pretty common pattern that you're going to encounter. Does it allow interoperability? Yes, it does. What you have to realize, though, is that you're then restricted to the devices that you can run your code on, right? I mean, it's not going to run CUDA code on an ATI device. It's not going to run CUDA code on a DSP. We have plans to add additional constructs in future specs that will give you better support for that, but you can call into, it's basically like calling into assembly level code from an existing OpenMP region. You're allowed to do it. It works. The spec is defined in such a way that you know what data is there and you can operate on it with your CUDA code. The reason I make the slight reserved response is that there are things that one can do to make it easier to use. It's not supported to the maximum extent. It's enabled, it's not supported, is what I would kind of say. It goes back to some programming language concepts, right? Like you can write object-oriented code in C, but it's not really supported. So as I was saying, so you know, we've got SSE and AVX, and we've got SIMD units on Blue Gene devices. If you think about it within a thread warp on a GPU, it's really a SIMD device. So we've got SIMD devices all over the place, and actually already have their own sets of directives for making use of SIMD devices, but they're not standardized. Well, now they are, and so that's why what the title of the slide is, it's reminiscent of our roots, because this aspect, although it's really significant, and I expect people to make a lot of use of the SIMD support in OpenMP, it's not groundbreaking new stuff. It's taking, you know, going back to Paul's earlier saying that the original OpenMP was really saying, okay, let's all spell this stuff the same way. And a lot of what we're doing with the SIMD stuff is let's all spell the SIMD directives the same way. Okay. So anyhow, so now you can take a loop and put a SIMD pragma before it, and that tells the compiler that it should be SIMDized. All right. And so that means that you're going to take the loop, break it up into chunks, each of which is going to be put onto lanes of the SIMD device. It will create a new data environment, and then you get some clauses that allow you to control the data environment and how the loop is partitioned. So for instance, if you know that your loop has some sets of dependencies that mean you don't want to chunk it up in anything larger than a certain length, certain size of chunks, then you can say, all right, this is the maximum size of the SIMD chunk that you should use. The compiler may choose to use a smaller SIMD chunk depending on what size device you have. All right. In the interest of time, I'm not going to go into this, but linear is basically what you want to use, and is now the default for single loop that you SIMDize for the iteration variables. You can specify alignments, and you can, again, still say things are private, last private, and reduce them, and you can collapse multiple loops into a single SIMD loop. All right, so similarly to wanting to tell the compiler that a function needs to have a device version generated, you may also want to generate a SIMD version of a function. All right, and why would you do that? Because if you encounter a function inside of a loop that you've SIMDized, what's going to happen? All right, well, if you're lucky, the compiler will inline the function and then be able to SIMDize all of its operations, and that's very hit or miss, and it's going to depend on the size of the function on whether or not the compiler will try that. The compiler could try to generate SIMDized versions of the function. That's almost certainly not going to happen, right? Because first of all, it would have to find the definition of the function for you, and second of all, it would have to believe that it actually could generate SIMDized versions. So more likely what's going to happen is that each of your SIMD lanes will issue a function call, all right? And you basically lost the advantages of running SIMD code once you hit that function. So that's why you want to go and, again, decorate your function definitions and declarations with the fact that they can be SIMDized. All right? And you can actually specify multiple SIMD declare directives on your function definitions to be able to tell it to generate multiple different SIMDized versions. So that way, if you're specifying a length or alignments, you can actually specify the different ones you might need. Here, the SIMD length actually is prescriptive, so it will actually generate a version that's targeting a SIMD unit of that width. And so again, we have combined directives. So if you can call your SIMD, for SIMD, actually this is backward. So first what you do is you divide the loop into chunks that you run across the different threads, and then each of those chunks is divided into SIMD chunks. If you specify a schedule that has a chunk size of 1, then you won't have anything to be SIMDized. All right, so this is kind of You use carefully, because if you specify, you will get what you specify. All right, so in 3.1 we added some very basic support for Affinity. So first of all, we defined OMP num threads to be such that you could specify the team sizes at different nesting levels. And we also created a environment variable that you could say, I want my threads to stay where they start executing. All right, so this OMP proc bind. We've now added significantly to the OpenMP Affinity support. So now instead of just being able to specify true or false for OMP proc bind, you can specify master, close, or spread. You might be familiar with some of these. So master says put the threads in the next region as close as possible to the, on the same place as the master thread. All right, and a place is implementation defined, and you can control what it means. So it might mean a NUMA domain, or it might mean a hardware thread, and that depends. Close means basically put it as close as you can to the master thread, but then don't fill it up, so move along to the next place as you go through. And spread means spread them apart as far as you can. And then there's the OMP places environment variable, which now allows you to specify what the places are, basically, that are being controlled by this. And the expectation is the implementation has to provide sensible defaults for the places. Importantly, as you're going along executing, where you want your threads to be bound may change dynamically. All right. So before, we allowed you to lock your threads down to the processor that they were on, or the hardware thread that they were executing on, and that was it. Now, when you come to a parallel construct, you can actually say, okay, I want the affinity support to be like this. So deal out the threads to the processors in this way. If you have a NUMA machine, say, with 4 NUMA domains, you could run your first outer parallelism with 4 threads and say spread them apart, and that's going to put them around on each of your NUMA domains. Subsequently, in your inner parallel regions, you could say close, which will then execute the threads within that NUMA domain, within the NUMA domain associated with each of the master threads of the nested regions. All right, and you can go and find out what policy you have currently. So, and I kind of already described what the different policies are. So, when I saw the show of hands earlier, we seem to mostly have C and C+ programmers, so I'm not sure that very many people here care about the Fortran stuff, but people who do care a lot. We've gotten a lot of the support for Fortran 2003 in place. We don't fully support 2003, so we have a list at the beginning of the spec that says these are the things that are not supported in 2003, and everything else is. I expect by the next version that we release that list will become empty, and it'll just be fully supported. All right, so I already kind of described this. This is the task group construct where I specify a structured block, and now in here I'm going to start creating a bunch of tasks, and I'm guaranteed that any tasks that I create off of this dynamic execution path will finish before I get past that point in the program. So it's a deep synchronization, and so now OpenMP supports both deep and shallow synchronization of tasks. So we also added the depend clause, which, as I said, actually allows you to specify that this task cannot execute until that one is completed. And so it's a point-to-point synchronization for tasks. So we're already, right now, we're busy adding examples. So one of the things we decided to do was separate the example, what had previously been the examples appendix in the specification, to a separate document. All right, and there's a variety of reasons for that, not the least of which that we want to be able to update the examples document much more frequently than we update the specification. So we can add more examples as we go along. And we're currently in the process of generating examples for the new features that will be added to that examples document. Nonetheless, we already are starting to figure out what we want to do in next version. What that version will be is kind of up in the air. We have several things that we know we would like to do, but if you try and make something perfect, you never release anything. So that's why we were ready to release what we have. So we may have a 4.1, but we also have another large list of things that we would like to add that would be fairly significant feature additions. And so those would come up in 5.0. I expect that we'll be fairly well underway on this exercise by November. In fact, we have a meeting in September, which I expect us to have pounded out pretty well what our priorities are. So what sort of things are we considering for 5.0? So one obvious thing is support for memory affinity. I can pretty much guarantee that the next version of the OpenMP specification will include support for next touch. It will hopefully include some more advanced ways of specifying relationships between computation and data. There's a number of refinements. I've mentioned some already with the, having more support for escaping into native device code, but there's a number of other things that we could add for accelerator support. One of the things in particular that we're considering is how would you support having multiple kinds of devices, all right? Which, if you think about it right off, the obvious example is, well, you have a GPU and a Xeon Phi, except that seems kind of stupid. But more likely is you might build a system where you have multiple processor types because of the way chip development is going. You may also, if you build a system out of DSPs, you would quite likely have multiple kinds of DSPs. In fact, a significant contributor to the device constructs were the folks from Texas Instruments, and their interest is in the whole thing is strictly from the standpoint of supporting DSPs. And so they often do have multiple device types. All right, so one thing that we've talked about is transactional memory. That's of interest to us with BlueGeneQ systems, and also if you're familiar with the announced plans for Haswell, it's another thing that might be of interest. There's still other things we could do with task and thread synchronization. Another thing that's kind of related to that list is the concept of futures, which may end up coming up for the next thing. Very far along is actually doing some things to improve the support for tools, for debuggers and performance analysis tools. Anyway, if you have any ideas, any things that you would like to see in OpenMP, we're very open to hearing about them, and now is a good time to tell us about them, because now is when we're figuring out what we're going to do. Well, the statements that were made by those who formed OpenACC, it's a long story, so I won't go into all the ugly details of it, but that they made when they started OpenACC, where they started it from is part of the ugly story, was that their intent all along was that it should go away once OpenMP added device support. Now they make noises differently than that. My expectation is OpenACC is not really a broad industry standard. All right, it's actually a very narrow standard of primarily targeting one set of devices. It reflected a lot of the early thinking of OpenMP for how we would support devices. What OpenMP has done is similar in many ways to what OpenACC supports. It's different in that our device constructs specifically allow you to use all of the OpenMP constructs within a target region, all right? Whereas OpenACC has no real interoperability with OpenMP or any other mechanism for parallelism on the host. All right, so basically with OpenMP you can have your conditional for the target directive say, no, I don't want to execute this over there, all right, but I still want to execute it in parallel on the host. Anyway, so why did I go into that? Because that's a pretty significant difference from OpenACC. That's not going to ever change. So we're never going to pull in exactly what OpenACC does. Things that we're more likely to add are actually things that are more similar to things you see in OpenCL, where you can actually go and query the runtime system as to what the characteristics and capabilities are of the device that you might be targeting. All right, because that then can guide how you want to split things up, how you might want to parameterize how that's set up. But that doesn't exist in OpenACC or OpenMP at this point. Most of what you can do in OpenACC you can already do in OpenMP pretty much. We only have sort of preliminary implementations of the OpenMP stuff there. Cray has done a fair amount of stuff for it, but there's been a lot of changes as we got to finally finishing it up. According to their representative on the language committee, who actually is the co-chair of the accelerator subcommittee, the performance is pretty much comparable to their OpenACC implementation. In his opinion, at this point, OpenMP gives you a lot more flexibility and a lot more freedom as how you code things, all right? So there's potential for greater upside with OpenMP, but there's also potential for finding more pitfalls and getting lower performance. So you might have to work a little bit harder right now with OpenMP than with OpenACC. So that actually is another potential topic for extensions. All right. Basically, can you distribute a loop across multiple devices? Because in some way the host is its own device. And it is essentially, but the way we've worded things in the spec, it's not exactly treated as a separate device. It's an interesting topic. I've actually done a lot of research with some folks at Virginia Tech on how to do that and how much you can get out of that. So this safe-len clause is just saying exactly that. At this length of SIMD chunks, I guarantee you that it's vectorizable. All right. And so compiler, you ignore. You don't look there and say, oh, they're dependencies. So the SIMD support is very, very consistent with what already exists in OpenMP. So remember with OpenMP, when you say parallel for, when you say OMP 4 on a for loop, you're telling the compiler, it's safe to put this across threads. And if you're wrong, it's your fault for writing a broken code. Right? The compiler will do it, and you'll get broken results. All right. On the other hand, the compiler doesn't have to analyze it and determine that it's safe, which is often what prevents you from getting parallelization or vectorization. So being as we only just approved it 2 weeks ago, there are no compilers that support 4.0. Where do people stand on it? So Red Hat has recently joined the OpenMP ARB, and they've been very actively working on the implementation in GCC to support 4.0. How far along they are exactly, I'm not certain, but given the sorts of questions they were asking, they're clearly pretty far along. My guess, without having had them confirm this, is that they will probably have a version out by the end of the year that supports 4.0. Intel is pretty far along on a number of the features. They're probably, 9 months to a year from having full support from what the head of their compiler team has said. If you have a good relationship with the Intel folks, you could probably get a beta version that would give you support for a number of the features. They've been particularly looking at using the device constructs for Xeon Phi systems. So you could probably get something that already supports that. So Cray is also fairly far along, but again, giving full support for the spec, there's a lot there. So I think very few of the implementers have gotten very far on the task-dependent support, for instance.